everything is pretty much the same as what we talk about here, very much the same. Okay, except instead of using, I think everything is the same because you're going to use a Z score here, so it's going to be the same. The conclusions are going to be the same as well. Any questions there so far? Any questions here?
Would the
yes
HO and the HA be 15?
Okay, so Amy, right? Amy said it's going to be 15. You are absolutely right. It's going to, so 15 is going to be there, but I wouldn't say, so, okay, so let's see. So you probably don't want to write H0 is 15, right? So this is not right. You have to set it up properly, okay? Okay, so let's take a look. Remember what we did earlier on? So how we set it up early on? You see how we did it here? Or maybe here? Right, so you have to use the right symbol. So those are important. Okay, so Amy was trying to say 15. Maybe Amy can help us, to maybe tell us a little bit more. So what is the data we are dealing here? Is it numerical data or is it categorical data?
Numerical.
Numerical. Why do you say it's numerical then?
Because it's like the amount of time it takes for them to like do the telephone call.
Yes, absolutely right. Absolutely right. Okay, so it's about a time, right? Time, it also provides the units as well. And so that means how much time it take here for a survey. So this is absolutely numerical data, right? Okay. So for categorical data is typically yes or no, right? We are not talking about people who participate in this survey versus who don't, right? So those are different numerical data. And okay, so let's try to fill in the blanks before we start working on this hypothesis testing. I think this part is very important because we know which, there's a bunch of formulas we're going to use, and the formulas I've already written down there, and you can also check out here. The formulas are the same. Hold on a second. Where is it? Yes, you can see this one. So hypothesis testing, you can see the formulas are all given here. You probably are going to write these formulas in your note card as well. I absolutely recommend you guys to do that. So in order to plug in all the numbers into the formula, it's very important that we know what those numbers mean. Maybe we can start with mu. So what is a population mean here? Do we know what the population mean is?
15.
15. Okay, let's see. I think we are comparing mu with 15, right? We actually do not know what a mu is. If we know what mu is, I wouldn't ask you to do a test. Okay, you see, so mu is not known, and the reason is because if just say, okay, hold on a second. If mu is 15, why are we doing a test, right? I know something, for sure is already 15, and I wouldn't ask you to do a test because this test is going to be about a mu, right? You guys probably know this is going to be mu. So we do not know mu. We do not know mu. Great, so 15, I don't know. How about X bar? What's the X bar? X bar is sample mean. What is a sample? It looks like you go out there and collect 35 surveys. So 35 is, this part is easy. So 35 is gonna be probably the sample size, right? Sample size, zoom in a little bit. And what is X bar? Do we know what X bar is?
Oh. 17.
17, great. Okay, so 17 is here. Okay, how about sigma? Sigma is given here, right? 4. Significance level, alpha. So everything is given here. You guys should write this out on your own, right? This part, you should write out this. Okay, so significance level is given here, 5%, right? Okay, so let's set up and, okay. So in order to set up the null and alternative, we know it's going to be, because we know it's numerical data. If it's numerical data, is always about mu. So the statement should be about mu. The statement should be about mu. And in order to set it up, I would highly recommend you to start with the alternative. I wouldn't say this works 100% of the time. This method, this approach, starting from alternative is going to help you maybe 90 or 95% of the time. So you probably want to start from here. So alternative is your research question. That's something you try to compare. So what are we trying to do here? What are we trying to do here? What is the research question? Anybody wants to give it a try? What's the research question?
I think it's asking for if the current rate of where the mean is right now is acceptable.
Yes. Let's see. So let's see. So you are only gonna charge a premium rate.
Yeah.
Yeah, whether it's acceptable, right? Okay. So I'm gonna write it out here to help you guys see how I solve this problem. So so is the premium acceptable or not? So when would you charge a premium? You only charge the premium if what did the question say? If a longer mean time is necessary, you're going to charge a premium. So you premium is acceptable if you have to wait longer, right? So the mean survey time is long, right?
And so we're trying to find out if it's more than 15 minutes, they should be charged the premium.
Yes, absolutely right. You are right. Okay, so I'm gonna rephrase what Amy just said. So premium is acceptable if a mean survey time is long. Okay, so I'm gonna just change it this one too. So mean survey time is just mu, right? If mu is too high, we're gonna charge a premium. Okay, so how high is gonna be considered high? I think they were comparing with 15, right? I think Jackson, or maybe Jackson said it was 15. Mu was 15, or maybe Benjamin was saying 15. So we were comparing to see whether mu is too long, mu is too high. So mu is 15. So premium is only acceptable if mu is more than 15. And this is something that you try to test. You try to see whether it is true, right? Remember, alternative is a research question. So mu should be more than 15. Is this part clear? I know the very first time you learn about hypothesis testing, it can be really confusing because what exactly is the statements we have here? There's a no, there's an alternative. The research question here is always something I try to test. We try to see whether premium is acceptable or not. So we want, when is it acceptable? It's only acceptable if mu is high. And how high is going to be considered high? If mu is more than 15, that's going to be considered high. That's why you go back to here and fill in more than 15. Right? Okay. So let's see. So if mu is more than 15 is the alternative, what do you think is the null then? What do you think is the null? The null statement is going to be
less than or equal to 15.
Yes. So we have already set up the null and alternative. So what kind of test is this? What kind of test? Is this an upper tail or lower tail? And how do I tell? This is an upper tail, very important. Okay, so how do I know it's an upper tail? I know it is an upper tail because the alternative is more than. If the alternative is less than, this is going to be a lower tail. But what we have here is more than. So this is an upper tail. Upper tail. So this is very, very important. Because why do I keep on emphasizing this is important? Because if you cannot tell whether it's an upper tail or lower tail, and you're not sure how to use this formula. Okay, so you don't have to use the formulas given here in the table. You can use you can sketch a bell curve, which is what I typically do. But just say you get super confused, you don't have a clue, and you probably want to refer to this table to do it. But this table requires you to be able to distinguish between a lower, upper versus a two-tailed test. So this is going to be helpful if you have, if you feel like the bell curve approach, which I'm going to demonstrate later on, doesn't work for you. So you better be sure you know how to tell the lower versus upper versus two-tail, right? Okay. So this is an upper tail test. Upper tail test, that means we are looking for evidence. It is higher than some threshold. And the threshold we have here is 15. And 15 is going to be the mu0, right? Mu0. And this is going to be helpful because we are going to plug in the mu0 into our formula, right? Okay. So we are done with step 1, and we're going to move on to step 2. Okay, so step 2. Step 2 is a test statistic. Okay, test statistic. So I'm gonna ask you, okay, so do you think it's a, what kind of test these days is this? Is this gonna be a z-score? Is gonna be a t-score? What do you think? Do we have population standard deviation? We have
Z-score?
it. Yes, sorry, Benjamin, what did you say?
A Z-score?
Z-score, yes, absolutely right. The reason is because, okay, so population standard deviation is given. Okay, so if it's a given, it's gonna be a Z test. And Benjamin was right. If it's a Z test, over here it's gonna be a Z-score, right? Okay, if it's a Z-score, I'm gonna write out the formula. Okay, so X bar minus mu 0 over sigma, right? Okay, once you do that, and we have already have all those quantities given down here, so you can plug them in, and you just gotta do it carefully. Okay, so let's try. So X bar is given here 17 minus mu 0. I think we talked about those just now. Is 15, as you can see here. And sigma is 4. And we collected 35 surveys, I think. Is it survey? Yes, telephone survey, yes. Okay, you just have to plug in all those numbers into your calculator, and I've already done the math, and it's gonna be 2.95804. I like to carry more decimals here. I don't want to, round it to 2 decimals yet, because this is a fairly intermediate step. You don't want to stop at 2 decimals. You probably want to carry 4. 4 should be good enough. So this is your test statistic. Okay, so I want to say a few words about test statistic. What this test statistic actually says, your data, the data you collected from those 35 surveys, they give you an average time of 17 minutes. 17 minutes compared to the threshold you try to compare with, 15. 17 is more than 15. Okay, this is the absolute sense. It's 2 units higher, 2 minutes higher. But you want to convert that to 17 minus 15, that's 2. You want to convert that 2 minutes in terms of standard deviation. We have already done that. This is fairly close to 3 standard deviations. So that means 17 minutes is actually 3 standard deviations above the threshold. This is really, really high. I mean, 3, we have already talked about empirical rule. 3 is fairly high. So that means 17 is actually much higher, significantly higher. That means we probably have a lot of evidence against the null. Okay, so I'm going to use a diagram to demonstrate what I just said. This is very, very important. Okay, I need a little bit space. So when you work on critical value approach, just like I said earlier on, there are 2 different approaches, critical value approach versus p-value approach, but there are 2 solutions. You can draw a bell curve like what I'm going to do next. Okay, so I'm just going to draw a bell curve. Okay, because Benjamin told us this is a z-score. Okay, so the curve I just draw is not any z curve. It's not any bell curve, it's a z curve. So you probably remember the z curve means a normal 0, 1, right? You remember that? Okay, so the center of it is 0 standard deviation. Okay, and what I'm going to do next is, okay, so I'm going to take a look of my evidence from the data. The evidence from the data is the z-score, and the z-score is 2.9504. I'm going to draw this evidence onto the number line here. Okay, so let's do that. So the test statistic we get is the evidence from your data. So this is your test statistic, and which is 2.95804, right? Okay, so this is the evidence from your data. And what is the 0? The 0 is something that you compare with. That's actually mu 0, and that's actually 15, right? You remember from the question? So what this question actually says, our data is much higher to the right of the threshold of 15. You try to compare it, it's actually about almost 3 standard deviation to the right of this 15. That's something that you try to compare with. It's much higher to the right, right? Okay. And so what we want to do next is I want to use this critical value approach, try to figure out what a critical value is. So the critical value is pretty much like a finding a cutoff point. So this is the number line we have. I want to find a cutoff value. So this cutoff value will help us to determine whether it's going to be considered too far away from this threshold. Okay, now it's tricky. Okay, you want to remember, you want to think about it. We are working on upper tail test. This is upper tail test. Okay, we are looking for evidence it is much higher than 15. So if you do want to establish a cutoff value, do you think your cutoff value should be on the left, smaller than 15, or maybe it should be on the right, more than 15 then? This is upper tail test. Do you think it should be on the left, or maybe the cutoff value, do you think or maybe it's on the right? For upper tail test, we are looking for evidence it is much higher than 15. Okay, do you think I should set up this boundary or maybe cutoff value on the left side of 15 or maybe on the right side of 15?
I think it should be on the right.
It should be on the right, right? It's only helpful if it's on the right. If it's on the left, it just says how small it is compared to 15. Now we're looking for evidence it's much higher than 15, so it should be on the right. Amy is right. I'm going to just write it down here. The cutoff value should be somewhere on the right. I don't know where it is yet. I don't know it. And so how do we find out this cutoff value or maybe critical value? You can go back to the first page we were working on. I've already told you. To find this critical value, you want to start with a significance level. You want to start with alpha, use the table to find critical value. So that's exactly what we're gonna do. And okay, so we want to start with alpha. Okay, so alpha is given us to be 0.05. I want to use this information. I use the Z table to find a critical value. Right, okay, so let's take a look how we can do that. Okay, so what do we need to do is alpha is 5%. So that means once we do establish this critical value, to the right of this critical value should be 5%. Okay, so we have the area which is 5%. Do you think you are able to find a critical value then using the Z table? Using what you know about Z table. Right, we should be able to do. I'm going to remind you, Z table only gives you the area to the left. Now we have the area to the right, which is 0.5. What do you think the area to the left is going to be? It's going to be 1 minus.
Value and subtract it from 1.
Yes, you are 0.95, right? 0.95. Amy is right. 0.95. Okay, so this is a probability. I'm going to look up my table. Okay, the table is here. I'm looking for a probability. Which is 0.95. It should be very high. It should be 1 point something. Okay, so let's take a look. So I'm looking for 0.95. And so you can see there are two numbers which are equally far away from them. And you probably remember we're going to use the average of those two. Okay, so the first one is correspond to 1.6. I think it's 1.64. 1.64. And the next one is 1.65. Their average is 1.645, right? Hopefully you remember this is one of the magical numbers we talk about in empirical rule. Okay, so we know that the critical value, I'm just going to go back here, 1.645. Not this one. It's very easy to, right? 1.645. Oh, I don't know what I was thinking. Okay, well, I really like, right. Okay, so we have the critical value, we have the test statistic. Okay, so I'm going to remind you, critical value is very much like the boundary point. You establish a boundary, a cutoff value, and the evidence from our data is actually higher than this cutoff value. Okay, so this actually says this is a cutoff value. Anything to the left of it is going to be considered close enough to the null. So this is the null, right? This is the null. This is the null. And if you are fairly close to it, you are going to fail to reject a null. If you are too far away to the right, okay, much higher than the critical value, you are going to reject a null. Okay, so this is exactly what we have here, 2.958. is higher than the critical value, we are going to reject the null. Is it clear how I arrived to this conclusion? Do you guys want me to say it again? If yes, just raise your hand. Okay, do you want me to say it again? Okay, I'm going to say it again. Okay, so actually I can write it out here. Okay, so our test statistic is 2.95804. This is more than 1.645, which is critical value. So therefore, we are going to reject the null. Okay, because unless you are fairly close to the mu, you don't have to be right here. This is the key. You don't have to be equal to 15 or maybe a standard deviation 0. As long as you are fairly close to it, you will not reject the null. You are only going to reject if it's further away compared to the critical value. And that's exactly what we have here. We have almost 3, which is higher than 1.645. You are going to reject, right? So you're going to reject the null, right? Okay, so this is a critical value approach, and we can solve it using a p-value approach as well. P-value approach. Okay, I need a little bit more space, so I'm going to just zoom in. Okay. So for p-value approach, what we want to do is we certainly want to find a p-value. And to do that, I'm going to start with the significance level. So this part I have already talked about that early on. Okay, so you probably remember here. Okay. To find this p-value, you want to start with a test statistic, and then you're going to use your table to find a p-value. So first is you draw the bell curve. Okay, so this is a 0, this is a z, and we're going to start with the test statistic. Test statistic is 2.950804. Okay, so how do you find the probability then? Okay, so for upper tail test, what you need to do is, okay, you just have to find the area to the right of a 2.845. This is true for upper tail test. Okay, it will not be the same case for lower tail test. For lower tail test, you're going to look for something to the left of it. But for upper tail, you're going to look for to the right. Okay, the probability associated is going to be this part. So this is the probability. You can find it using your z table. I'm not going to go over the details, and I think if you do that, you can see it's going to be 0.001415 using your z table. Right, okay, so you have the p-value approach. Once you find a p-value, you just want to compare it with alpha. So p-value is less than 1%, alpha is 5%. This is much less than that. So what would you do then? Are you going to reject the null, or you're going to fail to reject the null? You're going to reject, right? You're always going to reject if the p-value is small. This is very, very small. You are going to reject it, right? Okay. And so you guys should be able to fill in the blank here. Okay, so let's take a look. So this is a conclusion, which actually goes back to the context we have. Both the critical value and p-value approach, actually, if you take a closer look, both of them were able to reject the null. You should always have the same conclusion. You should always get the same conclusion for both critical value approach and the p-value approach. Regardless of which one you use, they should either all reject or fail to reject. They all indicate that we should the null. So what you should fill in the blank is gonna be you should reject the null, right? You should reject the null. Okay, at a 5% significance level. This suggests mu is, okay, so let's go back to the context we have. We rejected the null. Okay, so let's take a look. Okay, so this is what we have, the null versus the alternative. We rejected the null. When we rejected the null, we are gonna take the alternative. The alternative says the mu is higher than 15. The average waiting time is 15 based on those 35 surveys you took. Their average waiting time is 17. And statistically speaking, it is much higher. So the average survey time here is, okay, so you can come in here, is more than, okay, and is more than, okay. because the average waiting time is much higher. So a premium rate is it justified or is not justified? It is justified, right? Because mean average time is long, and then you can go back to here. It is justified. Premium is acceptable. So it is justified. You don't have to fill in any blank here. You don't have to, right? Is it clear how I solved this question? It looks like a little bit tedious, but once you get to the, you get the feeling of it, it'll be easier. Hopefully it's gonna be easier.